Okay, we'll get into chapter 8 now on propagation. And what we're going to take a look at is the structure of the ionosphere, talk about reflection and absorption of electromagnetic waves in the atmosphere, and study a little bit about the sky waves and the ground wave signals and sunspots and sunspot cycles, how to assess propagation, solar phenomena, and scatter propagation. I think in this session I'm doing, we're not going to do too much with the scatter propagation because I haven't done much work, if any, in that area. So just kind of to start off as a preface, what we're going to be looking at are ways the sun, the atmosphere, the earth all interact to impact the propagation of our radio signals. And it'll look like from the material that things are pretty static, and you can usually count on propagation to follow the general concepts that we're going to talk about. But really, nothing could be further from the truth. The whole field of propagation is pretty dynamic. It's driven by the energy and the mass from the sun, the interactions with the energy and the mass that comes from the sun with the atmosphere that we have, and all that's very dynamic, very variable. For example, it's not uncommon in the course of a short QSO that you have the signal that you're receiving can be pretty strong, 5.9 or better, and then it can fade away to almost nothing to where you can barely or can't hear it, and then it'll come back. Just a lot of variability, and that fading effect, by the way, is described as a QSB. So if you hear someone talking about sending a report to another station that they're having a QSB, that means the other station's signal is fading in and out. And sometimes you can be going along just fine, and for no apparent reason, it seems like the whole band goes dead or the whole band comes alive. So there's a lot of things that can happen. And so what we're going to be talking about is just kind of general understanding so you can figure out what's going on and make adjustments if necessary. And that's a big part of the fun. So let's take a look at the atmosphere on the Earth, and let's start down here at ground level. Excuse me. And the first, up to 6 miles to 30 miles is the troposphere. And that's where our weather is, the rain, the snow, the winds, and all that is in this part of the surface. 6 miles is about 30,000 feet, which is why jet aircraft tend to fly at that level or above to avoid a lot of this weather. And then when you go up 30 to 60 miles, you get a layer in the ionosphere called the D layer, and that's a fairly dense layer and has a big impact on absorbing electromagnetic energy. So obviously that would have a big impact on your propagation if you're trying to move electromagnetic waves through this area. And then the E layer is 60 to 70 miles up. The F1 layer is 100 to 140 miles up. And then the F2 layer is 200 to 300 miles up. That's up at the altitude that's considered low Earth orbit. And you'll have satellites. I think this International Space Station runs around here at this altitude. So it's essentially outer space, yet there's still a very low density atmosphere at that point. But in terms of what you can breathe, it's certainly a vacuum. And then to look at that in terms of day and night, We've got these same layers. We're on the sunny side of the Earth, and there's the D layer, the E layer, the F1, and the F2 layer. And then as you go from day to night, some things happen to the ionosphere. Um, One is the D and E layer disappear at night, and then the F1 and F2 combine into a single nighttime F region. So it would have, it's not too hard to see where propagation on the illuminated side of the Earth is probably going to be different than on the uh, dark side of the Earth. And the transition referred to as the gray line going from day to night will have some interesting characteristics as well. So if we take a look at how the various layers impact the uh, propagation of radio waves, this graphic here kind of shows if you have tower with um, frequencies that increase as we go to the left, so that at a fairly low frequency, the propagated electromagnetic energy is absorbed entirely by the D layer. So at this frequency, you're not going to get any transmission downrange to other stations. Then at a little higher frequency, the propagated energy can get through the D layer and can bounce off the E layer and be received at another station here at the end. This is called the skip. And generally, when the sky waves skip like this, you won't be able to receive the signal here, but a station here on the Earth will be able to receive it. So they're dead bands. And then again, as we keep increasing frequency, the reflected wave is higher and higher, giving you a longer skip uh, frequency and or longer skip distance. So there's less of a chance of having any reception in this area. But when you get out further, you can get reception, and then even higher frequencies have longer skip distances. An example of this is we were trying to work a station down around New Kensington, which is, I don't know, maybe 50 miles, somewhere in that range from here, for a contest. And they were transmitting on 40 meters, and we just weren't able to make contact with the station. And this is the reason for it, is that we were too close, and we were in that skip area, and was not able to communicate with that station. So we weren't able to get a QSO with that station. And then if you get high enough frequency, then there is you don't get any reflection back, and the signals go out into outer space, starting at approximately 100 megahertz. And this is why VHF radio is pretty much line of sight, because it's too high of a frequency. It's above the 100 megahertz, say it's in the 146, 147 megahertz range. And rather than bouncing back to Earth, its signal will just propagate out into space. So there are two types of waves that we're going to consider in propagation. The first one is ground waves. And generally, the ground waves follow the contour of the Earth. They can propagate considerable distances, and I'll show some examples of that a little later. Frequencies up to 2 megahertz. All frequencies will have some ground wave or near field capability. So really what you're looking at there would be like AM radio, low frequency, medium frequency, and low frequencies which can be affected by daytime and nighttime. And the other thing you need to be aware of is the long path and short path of a signal. And this graphic tries to show, say, if you're located here and you're transmitting to another station, this signal here is the short path, and the signal follows the great circle, the shortest distance on the surface of the Earth from your location to the other station. Then there's also a path that the signal will take, because you'll be transmitting behind the antenna as well in all directions if you have an omnidirectional antenna, and that'll be following the great circle around the other path and coming up to the station. So the station here, if you have a strong enough signal, it'll pick up this path signal as well as the long path signal, and you need a pretty good antenna and amplifier to do that, to get enough energy to go around the long path. But what this station will hear, if that's happening, is a bit of an echo, because even though the signals are moving at the speed of light, this distance being shorter than this distance, the long path signal will arrive at this station a little later than the short path signal, so you'll hear that echo effect. And this is just an example of where you can find some of this information. This is a page from qrz.com, and when you put in a particular call sign, search for the call sign, the website returns information about that call sign, name, address, quite a bit of class of license, its location, longitude and latitude, and it'll also show the bearing from where you are to that station. And in this case, it's a station in Ghana, and so this would be 93.3 degrees from where you're at here in Pennsylvania, and this would be the Great Circle path to that station. And then the distance is 5370, 5,370 miles, and the long path will be 19,486. You add those two together and you get the circumference of the Earth, which is around 24,000 miles. It also gives you other information, when sunrise and sunset would be at the other station in UTC time, and what zone it's in, ITU zone, CQ zone, and a bunch of other information. So that's just where you can see some information on the long path and the short path. That's what that is. The other thing that has a big impact on propagation is the sunspot cycle. And what that is about every, oh gee, I think it's 11 years or so, the number of sunspots on the sun will increase, reach a peak, and then decrease. And it's been pretty consistent every year. Where we are right now, or actually where we were when I became a ham in 2017, we were in the depths of the trough of the sunset cycle. So all the propagation was pretty poor. Now we're at the start of cycle 25, somewhere in here probably, and sunspot activities picking up, other solar activities picking up, and it's having more and more an impact on propagation. So we expect the propagation to become more active, which is kind of a double-edged sword. You get better propagation, but there are also other factors that increase, like noise and variability and that kind of thing. So some of the items that are measured to try to gauge solar activity is, one is the solar flux, and that's a measure of the sun's noise at 10.7 centimeters. There's a solar K index, and it measures or quantifies disturbances in the Earth's magnetic field. as it says there, during a 3-hour interval with a range of 0 to 9, with one being calm and 5 or more indicating a geomagnetic storm. That can disrupt communications. And the A index provides a daily average level for geomagnetic activity. Now, I've been trying to study this stuff here of late and get a better understanding of what impacts propagation. Uh, Ideally, it would be nice to be able to predict or forecast propagation, even if only for a few hours in the future, but I've yet to been able to come up with a way to do that or find anybody, uh, at least a quantifiable way that I could use on a day-to-day basis. Uh, so I'll just keep studying. Okay, took a little pause there. So here's an ARRL slide that talks about the measuring solar activity. And this is a plot of the monthly mean of the sunspot number. Here's cycle 20 back in the 60s, into the 70s, 80s, and up to January 2008. And so it's a little bit of a dated slide, but you can see there is quite a bit of variability uh, on a monthly basis within a cycle. Generally, for HF propagation, for daytime and nighttime, uh, daytime on 160, 80, and 60 meters, you're usually looking at local and regional communications 100 to 200 miles. And that's one reason, for example, in the emergency communications area with Aries and PEMA, a lot of the nets are held on 80 meters because for that type of communication, you're generally looking at wanting to cover the state and maybe the region around a particular state. And then at nighttime, you have the local, and also you can get long distance at nighttime on these frequencies, the lower frequencies. And best near sunset or sunrise when you get that gray line effect at one or both ends of the contact. And then generally speaking, 40 and 30 meters is local and regional. You get out a little farther. I would say just based on what I've seen, for example, on 40 meters during the day, you can generally go, say, get out to the Mississippi River, up into Canada, certainly down into Florida, and possibly a little farther than that. And then at nighttime, you get the short range 20 or 30 miles, that would be the ground wave, and then medium distance is 150 miles to worldwide. So 40 meters, and this is just my opinion, appears to be at this point in time one of the better bands to use for day or night communication for making contacts. And then 20 and 17 generally considered during the daytime, regional to long distance, opening at or near sunrise and closing at night. And then 20 meters at night is often open to the west at night and may be open 24 hours a day. And one thing we've noticed with Parks on the Air is that we go to various state parks and set up a portable station. And then Judy tries to communicate, call CQ and communicate with other people that are hunting for parks. And we normally start out on 20 meters, usually in the afternoon after we get set up. And that's when she's set up on 20 meters, she generally works stations west of the Mississippi. She'll be able to work when conditions are favorable. California, Washington, Oregon, Colorado, uh, those Pacific Coast stations and stations in towards Mississippi or the Mississippi River. And then after she's operated on 20 meters for a while, she'll switch to 40 meters, and that's when she gets the closer in signal safe stations east of the Mississippi. Uh, and you can see it clearly. There are programs or websites that'll plot your contacts from your log on a map. And you can see the band of 20-meter contacts and the band of 40-meter contacts. And then 15, 12, and 10 meters, primarily long distance when it's open. Here of late, it's been opening a little more than it had in the past, up to 1,000 miles or more, opening to the east after sunrise and to the west in the afternoon. And 10 meters often used at nighttime for local communications 24 hours a day. And that's one thing that we've been working with in our ham group, is using 10 meters for local communications for both single sideband and digital signals. Right now, when we do our Monday night net, a big part of that net is QSYing, which means changing frequencies from one band to another band, because that's something that needs to be done as a group in an emergency, because as band conditions change, you need to be able as a group to move together to another band that may be operating better. So what we do is we start off on our repeater, which is a UHF repeater. Then we go to a VHF simplex frequency. Then we QSY to a UHF simplex frequency. Then we go to the W3 CPA repeater, which is located up on the mountain between here and Clearfield. And it's probably one of the best, if not the best repeater in the area. And that's a VHF repeater, so we all check in on that one. And then once we close the VHF UHF part of the net, those of us that are equipped to do so, meaning we have UHF or HF radios and antennas, then we'll go to 10 meters and 6 meters at set frequencies and check communications. And the reason we pick 10 meters and we're looking at frequencies in the 28.300 to 28.500 megahertz range. The reason for that is that technician class licenses have privileges in that frequency range for single sideband communication. So if you're a technician and you happen to have an HF radio that'll work on 10 meters, you'd be able to communicate there as well. And also we go to 6 meters, which also has technician privileges. And then after that, we go to 17, 15, and 12 meters and just touch base with everybody, check in, and then we close the net. Now the last three, the 17, 15, and 12 meters, you need a general class license or higher to operate on that frequency range. So this is another look at the ionosphere and the impact on radio propagation. There's a couple of concepts that are descriptive phrases. MUF is maximum usable frequency, and that is the maximum frequency you can operate at so that you get the reflection back into the earth. If you go at a higher frequency than that, then the signal is lost to space. Now, to me, from what I've seen, that's more of a conceptual thing. I'm not sure I've ever seen an MUF meter or anything like that. but to know what that maximum usable frequency is. There are some places that will report it, but the ones I've seen aren't necessarily in real time that could help you out in looking for a frequency to use. Could be I just haven't found them yet. And then this is also showing the things we've talked about already, the skip or dead zone, where the signal will overpass a particular area. Shows the ground wave and the tropospheric wave. I haven't really caught any of these, but evidently there are atmospheric conditions that can exist where the signal could be propagated. I don't know, the best way to describe it would be in an atmospheric tube, so that you can get pretty long distances propagation before the signal comes back to Earth. Another key concept for propagation is NVIS, or near vertical incidence skywave. And what this is, it's a technique where you set up your antenna so that most of your signal, a lot of your signal goes almost straight up and then bounces back to the Earth. And you have a relatively small, let's say 50, 100, 150 mile area around your antenna that you're using the ionosphere to make contacts. And what that does is it allows you to be in close, work close stations, because the skip, you're not skipping over this area if the signal had been sent off, say, in that direction and then out. This is used quite a bit in emergency communications on 80 meters, sometimes on 40 meters, for that close-in statewide communication. And a lot of articles, a lot of different on NVIS, a lot of different ways to do it with different antennas, and it's kind of a little neat area to kind of study a little bit. You can see here the propagation pattern. This would be the vertical plot, and you see you get a lot of your signal going up rather than out, so that you get your reflection back to the Earth pretty near you. Now, if that one station in New Kensington had been operating on NVIS, we'd have been able to work them because the skip wouldn't have been there, and we've been able to establish a contact with them. And there are a lot of scatter modes. You probably read about these in the manual. Rain scatter, tropospheric scanner, meteor scanner, moon bounce. I thought moon bounce was pretty interesting, where you use a low signal mode to transmit to the moon, and it reflects off the moon and then comes back to Earth, so you can work the other side of the world if you get things set up that way. The one reason I haven't really explored any of these scatter modes is because my primary emphasis is emergency communications, and I just don't see where these are consistently reliable enough to count on, but they could be great fun to play around with. And then these are some graphics of the scatter modes, where this is an example of meteor scatter, where they wait for, or in times of a meteor shower, they transmit their signal and it reflects off the ionized tail of a meteor and then goes to another station. Now, I would think that would have to be kind of iffy, just on the frequency of the meteor strikes, even in a pretty heavy meteor shower. And then here's a graphic of the Earth-Moon-Earth bounce, where you transmit, say, in the northern hemisphere, bounces off the moon, and you can communicate with stations on the other side of the Earth. Gray terminator line. We take a look at this, and it's that transition from daylight to darkness. Um, you get, and it's not really repeatable, or at least I haven't been able to find it to be repeatable or predictable, but you can get some good propagation results during that time period, either in the evening or the morning. And then this is a look at that isotropic ducting, where the signal, rather than being refracted and bouncing off the Earth, it will travel in this region here and get to the receiver. But like I said, I'm not too familiar with these, and I guess I find them limited use, but would be good recreational ham activities. Now, there are a lot of tools available for getting a handle on propagation, so I thought I'd go over some of them that I've worked with, and there's a lot of other ones. And I would encourage you, as you get into HF, that you start digging around looking for ways to figure out what might be going on. Probably the one website that has, at least one of the first ones I ran across, was this hamqsl.com, and it's a kind of a solar report card. And the one thing you'll see here, you'll see on a lot of other websites, because this is shared on other websites, but it's solar data propagation. And what it'll give you, for example, the date and the time, solar flux index. That's a reading that generally tells you how, like we mentioned, active the sun is to a degree. The A value we looked at, the K value. The one thing I've been noticing is that this solar flux index, typically before we started coming up and turning the upside on this new solar cycle, I would see that solar flux index in the high 60s, low 70s. And then as we're getting higher up in to the next solar cycle, those are starting to operate in the low 70s or mid 70s to high 70s, indicating that the propagation is picking up a little bit. And then they have this little table down here that kind of gives you a qualitative estimate of what the HF band conditions would be at this point in time. Like here, they're saying that 80 meter and 40 meters fair during the day and good at night. These other bands are poor both day and night. Here's 6 meters and 4 meters looking pretty good. So this is, the way I'm doing it is I just look at it every day when I get on the air, and you just start getting a feel for how these numbers might impact the current propagation. Now, this is a YouTube site that's put together by Tamitha Skov, I guess it is. And she's a space weather meteorologist. And what she'll do is about once a week, she'll post a video talking about what's happening on the sun, and predicting a little bit what might be happening over the next few days in terms of propagation and the magnetic impact on the Earth from the sun. And she's pretty interesting, very enthusiastic, and that would be a good site for you to bookmark and just check her post when they come out. And like I said, mainly I think it's about a week, once a week she'll do it. Then she's got some other training videos that you can watch too to learn more about space weather. Here's another neat little website that Actually, Tom Somas, KC3IUB, pointed this out to me when we first got started. And here's the link to it. Hey, what's that? Um, Path Profiler. And what it is, it's a map tool that you can use. For example, I'm located here in Treasure Lake, and let's say I wanted to see what the terrain was from my house to a point in Brockway. So I establish those 2 points, and that's what this graph is here, where here's my location, and then the direct line of sight to the other location is shown here. It's 8 miles away, and you can see the terrain between me and Brockway is pretty prohibitive for communications with VHF or UHF, which is why I can't seem to pick up any of the repeaters up there and up towards Ridgeway because of this high mountain thing. So this is an 8-mile path. We used this quite a bit when we were trying to find a good location for the repeater in Treasure Lake to see what the path would be from a particular repeater location to a station. But this is pretty handy to use. Helps you understand why you may or may not be able to be reaching a particular station. And then this is a little study I did. The situation I had is that on FT8, which is we touched on this in the digital mode section, is a pretty popular low signal operating mode, digital mode for sending and receiving predetermined messages or a structured message format. And it's a real good tool for studying your propagation. And what I was noticing is that I was able with it was particularly easy for me to communicate using FT8 with stations in Australia. But it was extremely difficult, if not impossible, for me to work a station on Japan. And, it looks like it's a comparable distance, so I wanted to understand why that was. So I used that What's That Path website and did exactly the same thing I did with a station in Brockway. I established the 2 endpoints, and it showed me what was between my station and Australia, Sydney, which was 9,693 miles from my house. Now, I was able to make that contact pretty easily. Then I looked at Tokyo in Japan to my QTH, and it was actually much closer, 6,600 miles on the Great Circle. But what I saw was that between that station and my station, the signal would have to go over this part of Korea. I think that's the Korean Peninsula, Eastern Soviet Union. Up here is Alaska, and then come back to my house. So my current best theory is it's what's happening is because, say, if I'm using 40 meters, every few thousand miles, we're bouncing the skip. I think these mountains are disrupting my skip signal so that by the time the Tokyo signal gets to me or my signal gets to Tokyo, this has been pretty well interfered with, and I'm not getting enough signal to there. And it's due to these mountains that are in primarily these 3 locations. And so I took a look at Paris because I'm able to get into Europe pretty well. And you can see we're kind of up here on a high point. And if you can imagine the, say, a 40-meter signal bouncing out here, it doesn't have as much interference with it going east as I had going west over the Great Circle. Nothing easier excuse me, than skipping signals over the ocean. So that's another way you could use that tool to try to understand what you can and can't do. Then there's another technology, or I should say mode, that's included with the FT8 software package, and it's called Whisper, and that's stands for Weak Signal Propagation Reporter. So what I did, I was wanting to study propagation for my house on 80, 40, and 20 meters. So the way this program works is you set it up to transmit a whisper signal for 2 minutes. So the program actually sets everything up. You just tell it how you want it done, and then it'll receive whisper signals for 2 minutes. 2 minutes, and then it does this over a time period from the time you start the test until you end. So what I did is on May 11th this year, from 4:30 in the morning to 10 o'clock at night, I ran Whisper on 80, 40, and 20 meters for that time period. So one thing it gives you is a time graph, and this is here Eastern Standard Time, 4:30 in the morning, and then it goes through the day, and then here's 10 o'clock at night. And what these dots are the signal to noise ratio of stations that reported that they heard my signal. So what you can see here is that in the morning, and see what frequency is this, 80 meters. In the morning, there were quite a few signals around the world, or stations around the world, that were hearing my signal. And then as the sun came up, there were fewer and fewer, so that during the day, very few stations heard my signal. And then later in the evening, about 8 o'clock here, these stations start being able to hear my signal. So this kind of soft blue line kind of shows you how the propagation went during this time period. And you can see that just like we talked about earlier, 80 meters was much more effective in the dark at nighttime than during the day, although there was some stations that were able to hear my signal. So this is a map of these stations that heard my signal during this test. And you can see we even got a station down here in Antarctica. I think that was if I recall, it was a South Korean science expedition that picked me up. And, based on that graph we just looked at, most of these long distance signals were picked up during the evening and the morning. And then most of the signals are pretty close during the day inside here. So they give you a lot of raw data. You can do a lot of different graphs and plots and that kind of thing. And then this is looking at 40 meters, similar, fairly good station contacts in the early morning, and then it fades out during the day. And then right about sunset, the stations just come alive, and a lot more stations are able to hear my signal at that point. And that kind of goes along with the general statement we made earlier about 40 meters. And then here's the graph of that. You can see a lot of stations in Australia, New Zealand, South Korea's down there in Antarctica, got into South Africa. Now, then keep in mind, this is a weak signal mode, and the weak signal modes are very good at extracting the signal from even below the noise level. So this is probably the absolute best propagation map, and certainly, say if you were able to do it with CW, you would be inside of these maximums, because CW is a little less capable than Whisper, and certainly single sideband uh, is not at all a weak signal mode. So its propagation effectiveness would be even closer um, to your station. So this is kind of, it's not really a good predictor, but it'll show you how far you'd absolutely be able to get at different points of the day. So as I look at 40 meters and then 20 meters, this particular day, it actually got pretty good during the day. And sometimes that happens, sometimes it doesn't. That's what I'm talking about on the variability. Um, but this shows you what 20 meters looked like on that particular day. If I ran it today, I'm not sure what I'd see. Could be something like this, or could be probably would be something a little different. And then here's a look at the stations that were able to pick me up. Um, Still in Australia. They had their ears on down there in Antarctica, into Africa, and pretty well into Western and Central Europe. So that was Whisper. Another tool you can use to kind of get an idea of what propagation uh, is doing, and this is updated in real time. There are websites that are ham radio spotting pages. And the way this works, if, for example, you make contact with someone, um, have a QSO, and you want to tell other hams about it so they can make a contact, um, you can go to one of these spotting pages. And this one happens to be dxheat.com. And what you do is first thing you have to do is you have to um, become a member. It's a free, you got to sign up, and then you log in, and then you submit a DX spot. And what you're doing there is you're reporting the frequency, the call sign, any comments, and the band um, for the contact you just made. Let's say you made one in Africa, and it's kind of a rare contact, so you wanted to let other people know, then you could put that spot out here, and other people could see where this station was on the band. They could dial in and try to have a QSO with the station in Africa. So this is updated about every 60 seconds. And what this is, this would be the last spot that was made. And the way it's set up, this is the station doing the spotting. This is the frequency he was on, frequency of the contact, or the call sign of the contact, comment, West Virginia, Putnam, the time and the date. And then the way I use this, I kind of look at how I'll count down, say 10 spots. 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 1800, and this is an hour ago. Actually, 55, no, 65 minutes ago. Because here's the current time, and the 10th spot was a little over an hour ago. So there's been about 10 spots given during that period. Now, the longer that time is, the least active, or at least this is my judgment, the least active the band is. If it was more active, there would probably be more spots, and so you would have a shorter time period for the last 10 spots. The other thing we use this for, as you can see here in the comments, this particular spot is for parks on the air. It gives the park number, and so if you're a hunter and parks on the air, you can go to that frequency and try to work this station. There's another POTA, quite a few POTAs. POTA's getting to be a really active activity on ham radio. There's a lot of people involved. You can see here This was just a random screenshot. How many POTA stations have been sighted or spotted um, during the day, and this is on 40 meters. The other thing you have on this page is solar activity or solar flux index 77. You can see that's kind of at the top end of the red stage, and then the magnetic activity, they give the K2 and the A3, so you can pick up some of your solar information here. And then this is another section where it shows the relative activity. I didn't select North America, but let's say you were in Europe. This would be telling you that 10, 15, 20, and 40 are receiving the most spot activities at this point in time, and those would be the more active bands if you're wanting to look for some place to operate. So that's a spotting network. There's a lot of different spotting pages. There's some spotting pages that have telnet capability that you can tie your logging program in during contests or just normal operation to see the spots in your logging program. Just a lot of neat, and all this is free, a lot of neat stuff on the internet, tools to help you get a handle on what the propagation's looking like. And then the other thing you can do, and I just took these snapshots when I was putting this PowerPoint together. This is the band scope on my Kenwood TS890S HF rig. And I think we've looked at this before, but what this is a shot of 80 meters. It's actually the general portion of the single sideband, where it goes from 3.8 megahertz to 4 megahertz. And what I'm looking for here are signals of stations that are transmitting in that frequency range. And you can see I really don't see any stations transmitting. Don't see much in the waterfall. So this would indicate that 80 meters isn't doing too well at this particular point in time in terms of propagation. So I may want to look elsewhere if I want to try to make a contact. So then I went to 40 meters, and you can see we've got a couple of stations here, but there's a lot of noise in on 40 meters at this point in time. So this is another indication that, yeah, you could probably work this guy, but this one's going to be a little difficult because of the noise. The signal is so low. And then at the same point in time, look at 20 meters, and you can see that the noise isn't nearly as bad. We do have multiple stations on the air, so this might be a good one to kind of fool around with if you're looking to make contacts with other stations. So that's another tool you have if you have a band scope on your radio. And that's about it. Like I said, or don't know if I said it exactly, but all this propagation stuff's pretty interesting. But I don't know that it's an exact science because of all the variability that goes into it. That variability is driven by the sun. The sun's just, just puts out tremendous amounts of energy and mass, and it's varying all the time. And that variation in energy and mass is continuously impacting our atmosphere and causing variability in our propagation. So it's kind of interesting, and a lot of the other things in ham radio are fairly cut and dry. I think this whole area of propagation requires a little more technique, I guess, in interpreting information and trying to figure things out. So I don't know anything else. That's about all I know. So I guess we'll close this video here. And if you have any questions, let me know. 73, and I'm QRT. K3SKS.